Good afternoon. My name is David Getz, and these are my colleagues, Fong Nguyen, Pete Thompson, and Darren Wolf. And the title of our presentation is Low Lignin Feedstocks, Improving Yields of Biofuels and Bio-Derived Chemicals. So before I get into the technology, I'd just like to give you sort of the 1,000-foot view of where we are in the biofuels marketplace. It's a multi-billion-dollar industry. It's growing very rapidly. But current biorefiners are squeezed between the high cost of their food-based feedstocks and what prices they can get for biofuels such as ethanol. So for long-term viability, these biorefiners, they really need to maximize their yields and they need to minimize our costs. And where our technology fits in is that our innovation significantly increases the yields of biofuels and bio-derived chemicals that they can make by reducing an undesirable plant product for the cellulosic bioethanol process. So first I'm going to give you a brief technology overview and then hand it off to my colleagues. So cellulosic biofuel is a specific type of biofuel. So I just thought I'd explain a little bit about the market before we go on. So in 2007, Congress enacted a renewable fuels mandate requiring out to 2022 these amounts of conventional biofuels, such as derived from cornstarch or sugarcane, a little bit of advanced renewable biofuels, and then a large ramp up in this cellulosic biofuel. So just to be clear, conventional biofuel is where you take sugar that's derived from food sources, such as cornstarch or sugarcane, and then you ferment that using yeast or something to make ethanol or biobutanol or something like that. In contrast, these advanced biofuels have a great potential, but they're really unproven. It's very uncertain if they'll be able to make a meaningful contribution to our renewable fuel portfolio. And now what we're really going to focus on is these cellulosic biofuels, where we take non-food plant biomass, such as from corn stover or switchgrass, and then we extract the cellulose, the valuable cellulose fibers from this non-food biomass. And that cellulose is a glucose polymer that you can break down, and then you can ferment that sugar again, just as you do in conventional corn ethanol. So our technology, developed by our scientists, is we refer to as TULIP. And TULIP stands for Tunable Location of Important Bioproducts. And just as in a regular tulip, the plant can direct, for example, red pigments to this part of the flower and white pigments to another part, and can direct woody biomass and chlorophyll to the stems and the leaves. Our technology allows us to direct the location and amount of important bioproducts to specific locations within the plant. Now, TULIP is a platform, and they've developed a number of different aspects of that platform. The first one we refer to as TULIP 1.0, which is a low lignin plant. And the reason lignin is important in the cellulosic process is for that extraction of the cellulose material. So the woody biomass consists of basically the valuable cellulose polymer fibers bound in a resin made of lignin and hemicellulose that we don't want. And it requires a lot of energy and heat and expensive chemicals to extract that cellulose. In contrast, in a reduced lignin plant, it just requires a lot less energy, a lot less chemicals to extract that cellulose, and you can extract more of it at higher quality. So our innovation is a genetic modification that tunes the location and amount of the lignin produced. It also has potential applications for tuning the location and amount of other important bioproducts, such as possibly lignin or cellulose itself. And as you can see here, we do actually have some quantifiable data, and you can see that there's a significant increase in the amount of sugar extracted from a low lignin plant as compared to a wild-type plant using the same process. And if you extend out the time, you can actually get quantitative extraction of the sugars. So the value of this is that it's basically you get more of the valuable cellulose, which is thus more sugar and more ethanol at the end, and you expend less cost in order to get that cellulose. And then finally, the cellulose is purer, and so there's fewer inhibiting co-products that inhibit downstream processes such as fermentation and enzymatic hydrolysis. Now, low lignin plants in general are actually not a new technology. But because using the TULIP technology, we can place the lignin exactly where it's needed and get rid of it where it's not needed, the innovation really allows us to get a low lignin plant that has wild-type viability and is perfectly healthy and has the same pest resistance and all the other qualities that, that are desirable for a commercial plant. It's potentially feedstock agnostic because our scientists believe that the mechanisms that they're using to perform the TULIP modification are actually conserved across all plant species. So we can put it in trees, we can put it in flowering plants, we can put it in grasses, we can put it in corn. And it's also product agnostic because your end result is still sugar. So we're just maximizing the sugar yield, and anything you make sugar from is potentially valuable through a cellulosic process using this low lignin feedstock. So in this slide, I'm just talking about basically the minimum size of this market. As we saw earlier, there was a mandated minimum of 12 billion gallons by 2022 for ethanol. But as my other colleagues will mention, there are other markets for this as well. But just using that, because we're able to extract more sugar for less input costs, we can reduce the cost of cellulosic ethanol by $1 a gallon. So that's a minimum market size of $12 billion. So we used a techno-economic model that's been published, and you can look at our assumptions, our scientists' assumptions for how we get to $1 a gallon reduction. And the way that breaks down is there's basically you get more biofuel per ton of biomass. So for every $1 that you spend purchasing biomass, if it's low lignin, you get more biofuel out of it. And the transportation costs are also reduced because that ton of biomass just has more cellulose in it. And then finally, again, less energy and less chemicals in the pretreatment process. Now, currently, our technology is actually very early stage. It's been, the proof of concept has been shown in Arabidopsis, which is a model plant system in the laboratory. And in order to increase the value of that, we really need to go into a model crop that is commercially relevant. And we also have intellectual property protection has been filed for.
Hi, thank you, Dave. Next, I'm going to walk you through the market assessment of our technology. Since our technology innovation is in very early stage of the supply chain, there are a number of end products that could benefit from it, and we evaluate the attractiveness of the markets through criteria such as the market size, if our technology lignin adjustment would enhance the value of the product, and how feasible it is for our technology to penetrate the current markets. Next, we look at a very high-level market analysis. We look at for big market, the biofuels market, biomass derived synthetic chemicals, animal feed, and paper. We eliminate animal feed and paper markets for the following reason. For the animal feed market, the product is priced on the amount of protein, and for the paper in the market, the product is priced on the dry weight ton. In both cases, there's not sufficient value added for the current markets to adopt our technology. We then take a deep dive approach to evaluate the biofuels and biochemicals market. For the biofuels market, as my colleague Dave mentioned earlier, 2022 mandate set the minimum limit for cellulosic biofuel at 12 billion gallons. Right now, the U.S. production of cellulosic biofuel is less than 1 billion gallons. Hence, we expect to see huge growth in cellulosic biofuels in the near future. I also want to point out that there are many complementary innovations that are being developed in parallel to our technology, such as enzyme and fermentation technology, soil development, crop rotation, that would help the U.S. meet the 2022 mandate target. Next, we perform the market assessment for biochemicals and market. And I have one word for you, plastic. So to our analysis, we find that plastic is a more attractive market for our innovation. Plastic has relatively big market size of $45.5 billion, but our plastic market is most comparable with our technology innovation, as the building block of bioplastic directly replace the petroleum-derived chemicals in conventional plastic products. Even though today we focus on high-volume commodity markets, I also want to acknowledge the low-volume specialty chemicals that also use biomass feedstock. As we take a closer look at the plastic market segments and realize that the most common building block for bioplastic is lactic acid. In fact, lactic acid market is the second largest global platform chemical market just after glycerin. And in 2010, it's estimated that lactic acid total about $650 million. And for those who are skeptical about market viability of bioplastic, we have good news for you. NatureWorks, among many companies, have commercialized their bioplastic products under the trademark name Ingeo. As you can see, as you can see, Ingeo, NatureWorks started as a joint venture between Dow Chemical and Cargill. Even though the market for NatureWorks Ingeo product is still relatively small, only around $200 million. They use the same building block, lactic acid, for a wide range of applications, such as textile, durable goods, packaging, and we also want to acknowledge the technical challenges such as the low melting point of polylactic. That is the biggest challenge that for market penetration right now. But as we see in the near future, those technical challenges will soon be resolved, and we expect a strong growth for bioplastic in the near future. Next, P will tell you all about the dynamics of feedstock industry.
All right, thanks, Fong. So as Fong has demonstrated, there's clearly a large and demand market for biofuels and for bioplastics, which our products can derive significant value from. However, it's important to note that our innovation is actually entering into a market at the other end of a complex and still emerging value chain for biofuels and bioproducts, with a lot of complex interactions that we really need to understand the dynamics of to really understand how best to bring our product to market and to commercialize. The three main areas within that value chain are seed producers, farmers, and the biorefineries. The seed producers themselves are really a highly consolidated market, dominated by large agricultural conglomerates such as Monsanto and ADM. These companies control a lot of the existing crop markets, such as corn and soy, and have a strong relationship with the farmers they sell to. There are, however, a number of emerging players focused on specifically on the bioenergy crops, such as Mendel and CITRIS, who we spoke to in researching our products and our technology. The next stage along is farmers. Farmers are a highly disaggregated, but very risk-averse group, and therefore are very concerned about innovation and have a strong relationship to the seed developers in terms of guidance on what to grow and what to plant, and also in terms of proof of exactly if new innovations are being brought to market, will it grow in their lands? And so they're really dependent on the relationship with the firms behind them. Finally, the biorefineries, and the cellulosic biorefineries in particular, are still a very emerging industry, with no biorefineries currently working at large-scale commercial scale at the moment. These groups really break it down into two types: the pure cellulosic players, who are purely producing cellulosic biofuels, and the mixed players, which are building cellulosic capacity onto existing corn-based ethanol production. For them at the minute, due to the fact they're still growing and are still quite small, they don't really exercise much market power on the farmers. However, we expect as they grow and gain scale that they'll really start to exercise more influence because of the importance of feedstock to their overall economic viability. The feedstock industry really breaks down into two key product groups: the corn stover industry and the bioenergy crops. Corn stover is really an addition to the existing corn industry, and therefore deals with a lot of the traditional players, the mature players, and also deals with farmers working on their prime arable land, which is obviously very highly valued land, and is also used for food production. They also get a relatively low return on the energy input in terms of the energy actually produced in final products. Bioenergy crops, on the other hand, is still a small and emerging industry, with new players entering as well as the large incumbents. And they grow on cheaper marginal land, which obviously allows the farmers to be a bit more, not necessarily risk-seeking, but a bit less concerned about new products and new crops coming to market. And finally, they get a much higher energy return on their inputs because of the reduced amount of fertilizer and other inputs required compared to corn. We identified a major complementary market development which we really need for our product to be able to come to market and be successful. And this is based on the fact that at the moment, farmers are paid based on the mass of feedstock they deliver. For every ton they get a set price. However, our product doesn't increase the yield. It doesn't increase the amount of tons of feedstock per hectare. It improves the quality of the product, increasing the amount of sugar you get out of each ton by about 42%. Whilst this is valuable to the biorefineries at the end of the market, it's not directly valuable to the farmers at this point. And so we really need the feedstock market to develop premiums for better quality feedstocks. And we identified the two key actions that were really needed to allow this to come into fruition as being biorefineries, as they grow, starting to sign long-term contracts with the farmers that they're contracting with for specific crops and being willing to charge a higher price because of the higher value they can get out at the other end. And this then driving a larger overall feedstock market, which allows the establishment of standards and for farmers to really understand the importance of quality to these biorefiners. Fortunately, there are precedents in the market at the moment that give us cause for confidence, such as in the beer industry, where brewers will actually provide specific traits and crops to their farmers, depending on what inputs they want for their breweries. And similarly, relating to food-based corn and non-food-based corn at the moment for corn industry. Darren's now going to provide some recommendations based on our findings.
Okay. So as it's been mentioned many times, this isn't a business plan presentation per se, but really the end goal for us as a group was to come up with a commercialization roadmap or framework for our scientists to think about and some recommendations for them moving forward. And so really, since it seems like right now that our technology is going to be both plant agnostic, there really leads to some interesting possibilities, and there's actually been some precedent for this business model. Essentially, you have the option of licensing your technology or your trait to an existing player, taking advantage of their distribution, their infrastructure, their capital investment that's already done, and collecting a royalty off that. Or you have the option of developing aspects of your technology and making your own business. And essentially, we found that for us it was really most useful to think about this debate along the lines of which particular crop you're interested in getting into. So for instance, right now, everyone knows that we're making ethanol in a traditional manner using like first generation ethanol. And so that's essentially coming from corn in the United States, and the corn stover, which would be the cellulosic part of the process, which is where our technology plays, is just essentially sitting on the field going to waste. So if you're looking at entering the corn market because there's already existing capacity and you would have a bolt-on cellulosic process, it's a much different proposition than a bioenergy crop. And that's because corn already has, big ag is well into corn. There's already many elite strains of corn seed out there. There's already a lot of traits built into what farmers are using now that they're not going to be willing to trade for, a simple low lignin or potentially more. So you could kind of license that technology to one of the big players and use that asset, those revenues from those royalties, to go ahead and develop your own bioenergy crop. And just for reference, we got the numbers we got from Mendel from taking a corn crop all the way to market was $200 million investment versus a bioenergy crop, which is $10 million investment, taking it to, just to give you some idea of the regulatory hurdles. So basically, the idea would be license the corn. It's an asset. It gives people money to invest. It gives people the faith to invest money because there's something there, and use those funds to develop your bioenergy crop, especially since our researchers are working on a platform, which is essentially that in addition to this low lignin that we presented today, they may be able to trade other things. And then the other thing is for our scientists is essentially that the financial value of their innovation grows significantly with each technical milestone achieved. And so in the near term, they should seek non-dilutive funding to go ahead and move their trait into a commercially important plant and then try to grow it in the wild, essentially. So here we are as far on the roadmap to commercialization. We're basically right here at proof of concept, and we have it in a test plant, and we have 5 years ahead of us before we're really going to understand and have it in full-scale commercialization. So it's kind of a confluence of a number of things, right? The 2022 mandate for fuels, it's going to take us 5 years to get a platform biochemical out there, a bioenergy crop, 10 years. And in addition to just the feedstock aspect of it, throughout the entire cellulosic process, there's basically like the enzymes, the capital equipment, the plants being built, and there's going to be iterations on that because, for instance, BP's building their first large-scale refinery in 2013. It's probably not going to be the plant that's ultimately going to be the one that propagates. So essentially that, take the money from corn licensing, develop a bioenergy crop, move it in tandem with the process engineering improvements, and by 2022 we'll be ready to go. And just a big thank you to everybody that helped us and spoke with us. Our team, I feel, was extremely lucky that everyone we reached out to in industry was extremely helpful. So here there are some notable names, and now we're ready for questions.
I see you had Ceres on there and as a contact. Did you have discussions with them about their interest in moving something like this to market?
We talked to Ceres. Yes, we didn't speak specifically on this product, but we spoke to them in general. And the contact we actually had was the person who often interacts with JB, and they have in the past. They keep track on the innovations and the traits that are coming out of JB, and do indeed look at this as a potential. So if we didn't go to Big Ag, in addition to going to Big Ag for corn, there is the potential as a lower risk of licensing our technology to a bioenergy crop company such as Ceres indeed as well.
Thank you.
I just wanted to add that they are considering, getting into this technology.
Any other questions? Oh, I know you.
So I don't think it was in this presentation, but in an earlier draft you had that if we do license this to Monsanto or something, it's just another, it's a trait that you add to an existing seed that has a lot of other traits, and it's kind of just a new SKU number, so very little money to be made really on our end. So, and that's with an annual crop. So how do you make money on perennials?
That's actually a very good question. Essentially, so the first part is whether or not you think there'd be money in licensing corn. So licensing to corn. Essentially, when we spoke with the people at Mendel, their entire goal was to make 3 traits that they eventually licensed to Monsanto. And they said that doing the NPV calculation of licensing those traits versus any potential business model they would have for going ahead and starting their own business, it wasn't even close. So if you could have 2 reasonable traits or modifications to the plant, chances are that licensing fee actually would not be a trivially small amount. And as far as making money off perennial crops, that's actually a very good point, because people need to understand this is not a crop that you plant once and then you plant the next year. So you wouldn't actually be selling the seed. You would probably, even in the event you started your own business, you would have to have some sort of essentially royalty system where you're paying to use their crop every year.
We're not alone in looking at this as being one of the key challenges with the bioenergy and the perennial crops. There's all the companies currently looking at this are trying to figure out how best to build a steady revenue stream on a crop that you only replant every 10 or 15 years. I may be wrong on 10 or 15.
A couple of questions. So can this trait be implemented into some other energy crops, for instance, sorghum, which is an annual instead of a perennial that a lot of companies are looking at, some of the ones you mentioned? Mm-hmm. And also, did you consider any other business models for shorthand purposes, using the farmers as almost outsourced production, where you sign up the offtake agreements and you provide the seed? And might that be a way to get around the perennial problem?
Sure. So I'm getting the nod from our scientists that sorghum is a potential application. So those annual crops could be a potential target for us. On the approaches, it's definitely something we looked at as being a potential approach. Is looking at, and we identified as well that Ceres is working with Novozymes. I'll pick the right two companies. Yep. Ceres is working with Novozymes around the potential of this back end, or the very start of the value chain, and the very end, really working together on building out this single process where it's all contracted through on the same grip and the value is split, rather than having this concern, as you mentioned, around how exactly you contract back from the refineries through to the farmers.
Any other questions? You guys know?
In the interest of time, I think we're gonna. If you have any other questions.